Okay, so now we're going to actually look at adiabatic cooling in mountains, and you can literally see the wet side and the dry sides. You can see where there's a little snow shadow effect going on, and where the anyway, watch. Here we go.
We've all seen clouds build up on one side of the mountain and then on the other side just dissipate into blue sky. Maybe you want to know why that happens. Like most natural events, this one has an impressive scientific term attached to it. It's called adiabatic cooling and heating, and it occurs because of changes in air pressure. Here's some time-lapse video that shows what happens. Basically, as a partial
And it's true, you've all seen it if you live by a mountain, and if you've ever been to by a mountain, you might have seen it. But that's why I'm showing it, because we have nice hills here, but this is not quite the effect we always see. But you look here, just as we go on, this side has snow on it. And look on this side, so it's cooling as it goes up and it's snowing, and it drops. So as the air pressure drops or increases here, it's drier. And you can literally see there's not as much snow. You do get a little bit of snow that'll come over the tip. It's not exactly at the top. And then you'll notice here it starts to rise again, and you'll get a little more snow. So you can actually, that's how it goes over each ridge. It brings up more and more water.
parcel of air encounters a mountain, it is forced upward. As air pressure decreases with altitude, the air parcel expands. Expansion causes air to cool. When the air cools to its so-called dew point, the water vapor in the air condenses and becomes visible as a cloud. If there's enough moisture and the adiabatic cooling is strong enough, it rains or snows. Essentially, the opposite occurs on the other side of the mountain.
But do you notice here, you can actually see the point at which condensation is occurring, because there's no clouds down here and there's clouds right there.
The cool air sinks and compresses. Compression results in increased temperature. When temperature rises above the dew point, the cloud dissipates into invisible water vapor.
And you can see it
In
actually
Wyoming,
disappearing.
especially in winter, most of the moisture-laden air masses come from the Pacific, approaching our mountains from the west. So as adiabatic cooling occurs, more rain and snow is dumped on west-facing slopes. As warmer, drier air descends on the eastern slopes, it accounts for another famous phenomenon of the plains, the so-called Chinook winds. So we've looked at clouds from both sides now. Knowing why they form and disappear does not diminish their beauty. If it weren't for our mountains and the dynamic processes that occur, Wyoming would be a much drier place and, frankly, much less interesting. I'm Tom.
Okay, if you couldn't understand that because it's a recording of a recording, then please take a minute and watch that video. It's also there if you want to watch it again. Okay, let's look at this. We can literally see the snow side. And then you get the dry over here. Look, there's really no snow on this side. These are your ski runs. This is literally a ski resort. They're packing the snow in there, and they've cut out a lot of the trees that are growing, so that you get these nice ski runs. You will see if you go up into any place, if you happen to be a skier, that your parents or your family or whoever it is that you live with has the fortune to take you somewhere else and go skiing in the mountains, you'll see dry and wet side. Denver is actually a desert technically. It doesn't get that much rain, but if you go high enough up in the out, you can get some snow. All right, here we can tell this side right here is the wet side. Clouds are forming, and you can see just a little bit gets over this side, but this side is going to be lush and green. This side is going to be desert dry, because it's also warmer, it's not going to condense, it's already had water run out of it, it's just much drier air. And here is a nice illustration of that. Water, as it condenses, falls on this side. As air pushes up the mountain, it cools to its dew point, releasing the water. And again, you get a little bit of overshadow here. And as it cools, it goes up. As it goes down, it heats up. And this is dry air descending. Almost always hotter on this side than on that side, in fact, unless there's a big valley and it stopped here. So you can't go all the way back down to the same elevation. Otherwise, it will always be warmer on the dry side. And here's the dry side of a mountain. And there's little microclimates. You can see a little snow there and then nothing. But you can literally, this hasn't melted yet, right? But I can still see if it's the dry or the wet side, because I can see the lush green. Here it's green, so there's got to be a peak here where it falls down and then it starts to rise up here and then it falls down. So even though I can't really see the elevation from this vantage point, I can infer it by where it's lush and where it's dry. Where we're rising is where it's lush and where it's dry. So I can infer too that the air is coming this direction towards, from the bottom probably left to the top right. So this is adiabatic cooling. As we increase our height, our pressure decreases. As pressure decreases, our relative humidity increases. And conversely, as pressure increases, our relative humidity decreases. They're always inverse. They're one of the opposite of each other. As always, if you need help, the expectation is you're jumping on Zoom or you're talking to me in class, but you're asking for help.